Hello everyone, welcome to David Griffiths Electrodynamics. This is going to be problem 4.11 from the book. And real quick, if you're new to the channel, welcome. Feel free to subscribe to the channel for more videos like these. If this video helps you out or any of my other videos have helped you out, please leave a like on the video. That will help me out greatly. And if you want early access to videos or typed LaTeX solutions to these problems, you can look at the membership options on my channel. So anyways, I'm going to jump into the video. Let's look at the problem statement. Here we are. So we have a short cylinder of radius A and a length L, and it carries a frozen in or permanent uniform polarization P that's parallel to its axis. We need to find the bound charge and then sketch the electric field for the cases where the length of the cylinder is much greater than the radius of the cylinder, the case where the length of the cylinder is much smaller than the radius of the cylinder, and then the case where the length of the cylinder is about the same as the radius of the cylinder. And then it kind of goes into a little thing saying like this sort of material we're talking about here is called a bar electric, or an analog version, the electrical analog to a bar magnet, essentially. All right, let's look at this. So we have a cylinder. It has a radius of A and a length of L, and it has a uniform polarization parallel to its axis. So it's just going to be some constant K along the z hat direction. So at every point inside of the material, it's just some constant polarization pointing in the z hat direction. And it asks us to find the bound charge density. And you might ask, why doesn't it ask us to find the volume charge density? Well, if we have a constant polarization, the bound volume charge is given by the divergence of the polarization. Well, if we have a constant vector, the divergence of a constant vector is just going to be zero. The divergence of a constant vector field is zero. So there is no volume charge density. So we're only going to have surface charge in this case when we have a constant polarization. So that's a cool fact to keep in mind, is if you have a constant polarization vector, then you have no volume charge, just surface charge, bound surface charge. So our surface charge, our bound surface charge is given by P dot n hat, where of course n hat is going to be normal to the surface. However, we have multiple surfaces on our cylinder, right? We have the top surface that points, in the plus z direction. We have this bottom part of the surface that points, the normal points in the minus z direction. And then we have the surface of the cylinder itself, right? We have the actual wrapping portion of the cylinder where the normal points in the s direction, right? But our expression for the bound charge is going to be the dot product between P and n hat. Well, P is pointing the z hat direction, so the surface that's pointing, for the surface that's wrapping the cylinder, that surface is in the s direction, which in cylindrical coordinates is perpendicular to the z hat direction. So those two vectors, unit vectors, are orthogonal to each other. So the dot product is going to be zero. So there is going to be no bound charge density, or there's going to be no bound charge on the actual wrapping portion of the cylinder, but there will be bound charge on the top two surfaces, because on the top surface we have, or the top and the bottom, right? I just wrote this as a sigma b plus minus because when we think about it, it's going to be k z hat, and really, okay, let me write this as p z. So I'm rewriting this as p because I use that as the constant value instead of k. So that looks like an r now because of that thing. So p is just some constant p. So the top and bottom bound charges are going to be p z hat dot plus or minus z hat, depending on what surface we're talking about. So that's why I wrote plus or minus, because if we're talking about the top surface, which is the plus, then it's going to be p z hat. If we're talking about the bottom end of the cylinder, it's going to be p minus z hat. So we get plus or minus p is the bound surface charge of the cylinder. Then we just got to think about, it tells us to sketch what the electric field looks like. It doesn't ask us to find what the electric field looks like. So you can kind of use your intuition for this. And I went ahead here and showed that, there is no bound charge in the volume bound charge, because the divergence of this field is 0. Now, for sketching the electric field, it's really just going to be kind of intuition and thinking about what this looks like. So let's just think about the case where the length of the cylinder is much larger than the radius of the cylinder. So that means that the ends of the cylinder, if the radius of the cylinder is super small compared to the length, the ends of the cylinder kind of just look like a point, right? The length is, it almost looks like a long wire, I guess, with 2 charges at the end of the cylinder. Well, what does that look like? That's really just a dipole, isn't it? Right? Like, if you have this very, very thin, long wire, that's just the separation distance, and you have a charge at the end of the 2 charges at the end of the wire with an opposite charge, it's really just a dipole. So when the length is much, much greater than A, the ends just look like point charges, with sigma B being it with the bound charge density, with the charges at the end being plus or minus p pi a squared, because the charge would be the surface charge density multiplied by the surface area at the end. So this would be the expression for that, I guess, the charge at the end of the wires, plus or minus p pi a squared. But it just looks like a dipole. So essentially it would look like the electric field would be like the electric field of a dipole, like we saw from chapter 3, which is just going to be like a field that sort of loops around like this. It goes from the positive charge to the negative charge, and you would have these fields that look like this. It kind of would look like a bar magnet in a way. I'm not going to do a hardcore derivation of that. I mean, you could just plot the fields, I guess, of a dipole. Like, go find some 3D plotter and plot it, I guess, and if you want to see what it looks like. But yeah, that's essentially what it's going to look like. So for the case where the length of the cylinder is much less than the radius of the cylinder, so we have this like very tall cylinder, but not very wide, essentially. It's like, it looks like a little very skinny plate here. Sorry, I'm shifting that way up. But it looks like this little skinny plate here. And I could have made this even more exaggerated, honestly. I should have. But essentially, it's going to be like a very skinny, tall cylinder. And what's going to happen is that this just looks like a circular parallel plate capacitor. It just looks like a capacitor, essentially. You have like these 2 charged ends very close together, because A is very small, or sorry, because L is very small. And because A is very large, you get this sort of capacitor-like structure where the field is going to be fairly constant between the 2 plates, the 2 ends of the cylinder. And then as we know that the fields at the end of a capacitor like this will start to bulge out, and eventually you'll get these like circulating fields. If you're interested, like, go look at, you can kind of look at, Google the plate, like an electric field of a parallel plate capacitor, and kind of see what I mean. But this is essentially what it's going to look like. I just drew a rough sketch. The problem doesn't ask you to find the field. It just asks you to make a sketch of what the field might look like, essentially. So then, for the case where the length of the cylinder is approximately equal to the radius of the cylinder, I mean, in this case, I don't know what the exact field is, of course, but just from my intuition, it's not going to be exactly like a parallel plate capacitor, but I imagine it's going to be fairly close, because you're scaling the length and the radius by the same amount, and so it should be approximately constant. And you basically have these charges on the end here, that stay the same distance apart effectively. Well, they don't stay the same distance apart, but based on how you scale the cylinder, the amount of charge scales linearly as you change L and A. So the field should be approximately constant, but I suspect that it will start to bulge out again as you get closer. I imagine it'll start to bulge quicker than it would in the parallel plate capacitor case where it's much more squished. But that's my kind of just intuition. I don't know if that's right, but that's just what I'm going to say is correct, is that the field is going to start to be constant near the middle and then start to bulge a little bit, and then eventually near the tips of the ends, it'll probably start to have this sort of circulating kind of field effect where it wraps around from the positive to the negative end, kind of like a sinusoid or whatever, or what, I don't know what I'm talking about, but like one of those sort of magnet things with the wires wrapped around them. I don't know. Anyways, that's going to be it for this problem. If you guys have any questions, comments, or concerns, feel free to let me know in the comments below. As always, if you enjoyed the video, leave a like, comment, subscribe. And yeah, I hope you guys have a great day, and I'll see you guys on the next video.